So now we're going to talk about some of the origin establishment theorems that give us a definite integral. And so this is the definite integral definition right here, and it looks a little bit scary, but the main point here is that this is a really this is a strip of y value, and this is a really thin strip of x. So just like we said before, we're adding a whole bunch of little tiny strips. And if you add up all those little strips and this gets really small, that space where the delta x is really small, then you have the actual area under the curve. That's the limit definition. But you really need to know the integral definition. This is read the integral from a to b of f of x dx. And it's the area from the starting point to the ending point. And you're going to see this a lot. You're going to have numbers a and b there. And that's our definition of a definite integral. What we did before with plus c was an indefinite integral because we didn't know the actual function. What happens when you're finding this derivative, the c will be the same for both, and when you do the subtraction, the c's cancel out, so the c doesn't really matter. It's just always that area between there, and it's between the curve and the x-axis. Some definitions that go along with it. Area, obviously we've talked about that right from the start, so that is the definition for area. And it works for rectangles, it works for semicircles, whatever shape you have, any kind of function. A couple definitions. This one is kind of a duh theorem. The integral from one point to the same point is 0 because you're not going anywhere. You think about that, the area is nothing. This one is used some in different applications. If you go from right to left, it is the opposite of the area from left to right. So if you switch your starting and ending points, you get an opposite value. And then there's some properties similar to derivative properties that you can factor out a constant and it's along for the ride. You can leave it in or you can factor it out. And the sum and difference of different functions can be broken up. So you can break up an integral into parts so you can do each individual part. And we're just going to do some problems from page 279 in your book. And these are involving different properties and the continuity. So they're going to give you, they're not going to tell you the actual function, how to find it yet. We're not that far, but they're going to tell you different properties along the way. So the integral from 4 to 2, so you notice we switched. We have all these are 2 to 4. So the integral from 4 to 2, if you switch your bounds, you just take the opposite sign of what the integral from 2 to 4 is. The integral from 2 to 4 of 8 x dx, the 8 can be factored out, and it would be 8 times the integral of x from 2 to 4. The integral of x from 2 to 4, they tell us, is 6. So 8 times 6, this would be 48. The integral from of x and minus 9, you have to do a little thinking about this. So we can break it up into parts. We can break it up in the integral of 2 to 4 of x minus the integral from 2 to 4 of 9. Sorry, well, that is one that's given to us, and that's equal to 6. And they don't give us 9, but we could take the 9 and write it out front. They do tell us the integral of dx is 2. So 9 times 2 is 18. So that would be negative 12. And then let's go over to number 34. The integral of 2 to 2 If you're going to the same bound, that's always 0. Integral from 2 to 4 of 25 is the same as taking this 25 and putting it out front. And so it would be 25 dx. Well, the integral from 2 to 4 of dx is 2. 25 times 2 is 50. X cubed plus 4 would be the integral of x cubed plus the integral of 4. This technically has a dx on it, but I often forget to write it. The integral from 2 to 4 of x cubed, they said, is 60. The integral of 4 times dx. Dx from 2 to 4 is 6. So 4 times 6 is 24. That is 84. This one right here can be broken up into 1/2 x cubed minus 3 x plus 2 dx, which would give you 1/2 of 60 minus 3 times 6 plus 2 times 2, which would be 30 minus 18 plus 4, which is 16. So similarly, you can break it up. I don't have enough space down here. You can break up number 40 into parts. 10 dx plus 4x minus 3 x cubed, and plug in those numbers. As we keep going here, that says the integral from 0 to 7 of f of x dx. Well, from 0 to 5, plus the integral of 5 to 7, so we're putting the parts together, it will give you the total area. So 10 plus 3, that's 13. And here is 5 to 0. We can rewrite that as the opposite of 0 to 5, because we can switch the direction around. From 0 to 5 is 10, so we have negative 10. So that's using some of the properties. They don't always give you a function. They want to see, it's like a table problem with a derivative. They want to see if you know your properties. And then you can find different values from there. We're going to continue here. The interval from -1 to 0. We have the integral from -1 to 1. If you think about this as a visual, integral from -1 to 1, and then the integral from 0 to 1. So we know the overlap is 5. So the integral from -1 to 1, the whole interval, whatever that is 0. And then if you go over 5, we can combine those two properties and go from -1 to 0. So we're really going from, instead of -1 to 0, or from -1 to 1, we're going from -1 to, you can take away this part, which is, you're saying this is 5. So actually I should have drawn it. We don't, so from 0 to 1 is 5. -1 to 1 is 0. So that means the area over here has to be negative 5 because the whole thing is 0. If the right side is 5, the left side is negative 5. And then we say we want to go from 0 to 1 of f of x. So from 0 to 1 is 5. And then minus negative 1 to 0 of f of x. So we just said that was negative 5. For c, you can write this as 3 integral negative 1 to 1. So 3 times 0 is 0. And the last one is from 0 to 1. 3 from 0 to 1. 0 to 1 is 5. 3 times 5 is 15. So just using your properties, we'll mostly be using functions. We'll know what f of x is, but when we don't, we have to rely on what they give us.